our panel is going to be taking that, picking up from there and exploring further. And I'm going to just do a real quick overview of what's going to be talked about here. What are farmers asking about climate smart agriculture? And Mark here is going to share that from the extension perspective. Then we're going to talk about associating agricultural practices and land management with climate benefits. And Peter Woodbury at Cornell is going to talk about that. And then we're going to talk about using models to bridge from observation and management data to national scale greenhouse gas emissions. And Dr. Ogle and Dr. Del Grosso will be sharing about that. And then modeling U.S. greenhouse gas mitigation potentials of agriculture and forestry. And that's Sarah Orell from EPA. So Mark, I'm going to release the screen, and if you can pick up.
Okay, thanks for having me. So yeah, was asked to talk about, what farmers are asking about climate smart agriculture. And I've tried to boil that down a little bit because I think in some respects, there's a large segment of that population that really isn't even talking about it, quite honestly. And so one of the first things that I was thinking about as I was, kind of preparing some thoughts here, is what does it really mean to tell farmers about climate smart agriculture? And, a lot of these terms are things that have been talked about earlier today. They get talked about fairly commonly. And I would say that most, if not all, farmers have some familiarity or awareness with these terms, but I don't know that they always know exactly what we're talking about. Okay, so I'll just pick on sustainable agriculture or conservation agriculture because those two are probably some of the most common lexicon, right? But they mean different things to different people. And so I can talk to my brother and he will tell me that, he's farming and he's using conservation tillage. Yet if I go up to his farm, there's a lot of soil there and there's a lot of erosion that's occurring. And so I think they have different definitions than maybe we have of some of these terms. And, so I think part of, what we're hearing is they just want more clarity. We all need more clarity on some of these targets. Again, I use my brother as an example because he farms and I get to talk to him probably more frequently than others. But, when I talk to him, he's very interested in trying to do what's right. He wants to help and do his part, but he also wants to be very careful about not being placed with burdens from other segments of the economy, right? And so he is, very aware of, the burning of fossil fuels, with the field operations, the releasing of greenhouse gases through the production of fertilizers, those types of things. And he understands that that's part of his obligation is to be aware of that and to work to reduce those. But at this point in time, he would say, wait a second here, why do we need to have the burden of greenhouse gas reduction from automobiles or the industrial processes and other processes? And so that's kind of the framework or the background that I'm taking with some of this. And then as we think about being resilient, most farmers are farming because they're productive and they're profitable year in and year out. And to them, that is kind of that resiliency standpoint that, they're running a business and that business has to be profitable. So they're doing this and they're really working in a very, very complex cropping system, right? And some of the previous presenters have talked about the complexities, right? So when we think about it, we're thinking about, the complexities within that cropping system, but to a farmer, they not only have that cropping system complexity, but we also have to recognize that they're also, in addition to being, the grower, they're also the agronomist, the mechanic, the grain marketer, the procurement specialist. They're doing logistics. And so when we ask them to adopt certain practices, we have to recognize that they're trying to figure out how this one practice, not only fits into their own cropping system, but what else is it doing within their business model? So they've got to be balancing those things. And so some practices may be very easy. So, an example of that would be, moving into a split nitrogen program, right? So that's likely not having any impact on their tillage or their planting or their herbicide applications, right? It's simply moving the timing of that nitrogen application from 100% pre-plant to partial pre-plant, and then the remainder, in season. On the other side of that spectrum is something like cover crops that I've worked in for the last 5+ years, where all of a sudden when we're asking them to adopt a cover crop, we're now telling them that they have to change their herbicide program. They're more than likely changing their tillage system. They're more than likely changing their nitrogen program. And then they have to figure out how to terminate and establish these cover crops at a time of year when they have a high demand on their labor, right? So that these are very complex systems. There's a lot of decisions that go into them. And so, when we talk about new practices, frequently we get, how does this fit into what we're already doing? How do we balance all the demands on the system? Okay, and then I think it also helps to recognize that farmers are very capitalistic, right? So they're wanting to increase their profitability, just like Amazon, just like any other business out there, right? They're around because they're being profitable. Now we couple that profitability with increased productivity, right? And so that's largely just because it's a commodity-based system, right? And so they can produce and they can be efficient as they can, but their payment is based on a pricing that they're only influencing through basically how much is being produced, and that's being influenced by not only other factors within a single state or within a country, but also globally. And so they're really trying to balance this profitability with how do they do things in a more climate friendly way. And then the other aspect of this is they're always looking at de-risking their production. Okay, and so they're doing this through government programs. They're doing this through management practices, right? So we very commonly hear that they tend to apply more nitrogen than maybe is needed, but the risk of not having enough nitrogen is very, very high. And so that's just an example of maybe one of the areas that they use management practices to de-risk that production. And then they're really working at, quite honestly, that years of experience is part of that de-risk, right? And so young farmers, newer farmers, have a lot higher risk because they're kind of learning as they go. Same thing would be said as if they incorporate new practices. They're learning that new practice and how it's fitting into their system is a very risky proposition. And so sometimes it's easiest to continue doing what you've been doing because you know how to do it, you know how to de-risk it, you know how to manage that system. Okay, and so we have to recognize that that's partly what's going on as well. So maybe a little bit more directly toward, the title here is really focusing or thinking about, what those farmers are asking. So year in and year out, I continually get asked about decision tools that they can make decisions based, on the current situation. A lot of times, an analog year comes into the vocabulary of the conversation, right? So, when was the last time we had a planting season like this? What were some of the things that we could have done, right? So that's kind of, I'll call it a static way of doing that, or And then the other thing that we often do is kind of farm on the average, right? So we know out of the last 10 years that these practices have given us our highest productivity, highest profitability. So we're going to farm on that average and move forward that way. But if we have these decision tools that are very, very dynamic, now all of a sudden we can guide those in-season management decisions, right? So if we have a decision tool that can tell us how much nitrogen has been mineralized in the soil, how much nitrogen has been lost through the soil. And, as I look out my window today, it's starting to get cloudy. The rain is in the cards for later today, but yet I know farmers are out there applying nitrogen. So if we get an inch of rain, was that a great decision? Probably not, right? But how can we help them make that decision better, right? So can we help them change their nitrogen rates or change their nitrogen timings by having information that they can access in, so to speak, in the moment, because they're out there making decisions every day. Okay. And then the other thing that I get asked a lot about is, so what are the market opportunities for something other than corn, soybeans, or wheat? Right. And we're hearing, a lot of demand for wheat, especially, but other grains, other oil seeds, because of what's happening over in Ukraine right now. Right. But truth be told is that we have a system, at least in the Midwest where I'm at right now, where corn and soybeans and wheat can be grown very efficiently. And the markets for other crops just really aren't there. Or if they are there, it's kind of which came first, the chicken or the egg. They'll give you the market after you've got it grown, but yet if you are growing it and don't have a market, you have a lot of risk that's being put out there. And so I think farmers are willing to grow other things if they can do it in a very friendly way and know that they have, that market potential for them. Our infrastructure is set up so much so for, corn and soybeans in Iowa right now, that growing wheat, farmers will say, yeah, I can grow it and I can get good yields, but I have to grow enough to justify, basically holding a 40,000 bushel bin or hauling, truckloads away, right? So they have to be able to justify those in that perspective. And then the landlord-tenant relationship is very dynamic and does impact how we think about a lot of the management practices that we do. So yeah, it's very easy for, a farmer who is renting land to say, they're going to move into no-till or they're going to use cover crops. Those in-field practices are very easy for them to make, regardless of what, the landlord may be dictating. But when we think about, something like Bruno mentioned, as far as marginal land, that should not be in row crop production, it's not profitable in 8 out of 10 years. Now, all of a sudden, this brings in that landlord relationship, because those landlords, they're, in some instances, in a lot of instances, actually, they're reliant on the cash rent from the tillable acres of that field. And so a farmer that has a year-to-year lease or has a 2 or 3 year lease is not going to be able to take land out of production, put it into a CRP program, because now they've got the cost of doing that and they're still paying rent on it, so to speak. And actually with the CRP program, it's the landowner that gets the contract, right? So we have to recognize that there's some complexities there. And then the realization that as farmers retire, they still hold on to that land. And in some cases, they still hold on to the management of that land through crop share leases or other active management roles. And so as the younger generation does come in, they still have a hard time making management changes because of these dynamics. And we hear about these, and we're commonly asked, what types of things can we do? What resources do we have to help work with these landlord-tenant relationships? And so with that, I'll end, and hopefully we'll have time for some lively discussion as we get through the rest of the session.
Thank you so much for sharing that perspective. And, it all comes down to that, doesn't it? What works and what doesn't work for the farmer, and those, how to navigate those complexities. between tenant and owners and everything else. At the moment, let's move ahead. And Peter, I think if you can take control. And Peter, we're seeing your screen, but I'm not hearing you as yet.
Okay, can you hear me now?
Yes.
Great. Thanks very much. I'm going to be talking about associating agricultural practices and other land management with climate benefits. And the theme is a few things that we know that are really important and a few things that I think we may need to know in this context. So one thing we need to keep in mind is that most greenhouse gas emissions globally are carbon dioxide, but in agriculture, it's mostly nitrous oxide and methane. So for the US, we can see here that it's well over 3/4 of the emissions. We also need to keep in mind that greenhouse gas mitigation should be permanent, real, and verifiable. So Dr. Lyle talked about soil carbon as a bank, implying that it's not permanent. We can put it in and we can take it out. In terms of real, we want to account for all three greenhouse gases. And we also want to make sure that emissions don't just shift from one place to another or leakage. And then for some purposes, we want to measure or meter at the field scale or possibly at the regional or national scale. We want to track the progress. So we have modeling tools to address many aspects of climate change and land management. And we also have modeling tools and other information to address erosion, soil health, and adaptation to climate change. And I just want to kind of open the conversation here that we'll always be thinking about more than just greenhouse gases when we think about land management. We also need to be thinking about water quality as well. There are water quality issues, of course, associated with agriculture and land management. And we have tools to model and quantify these issues, but we may need to think more about connecting those with our tools for greenhouse gas monitoring and mitigation. We also need to think about air quality. So there are emissions from agriculture, such as ammonia, that can contribute to air pollution. So we need to be thinking about soil quality, as Dr. Lyle mentioned, as well as water quality and air quality. We also need models that support a range of practices. And what is a uncommon practice today may become a common one tomorrow, but there are always new practices being developed. And these range from well-known, Mark just spoke about precision nitrogen fertilizer management. So farmers can use tools such as Dept to optimize in real time that side dress application rate. But we need to think about our greenhouse gas models and assessment keeping up with that. In other words, if we're using that precision tool to really dial down the precision management, are we capturing that benefit in our models? So tillage is certainly a well-known topic, but it's also complex. We heard Mark say that one person's conservation tillage might not be another person's. There are many types of implements, many interactions with soil. And then there are other practices that are less well known. So silvopasture is producing livestock and trees on the same land at the same time. Here's an example from New York State growing black locust fence posts and black walnuts and grazing all at the same time. So our models may or may not be ready to handle some of these lesser known practices. Another practice turning to forestry is preventing deer damage so that we can have good forest regeneration and we can grow that healthy forest, which stores a lot of carbon. This example is building slash walls of the non-merchantable material to keep the deer out after a harvest and allow that forest to regrow. And I'll show just 2 slides here from a national analysis of the potential for land management, the Natural Climate Solutions Project that I was involved with. So this is showing the forest options, starting with reforestation or growing trees in former agricultural land, as well as natural forest management. And there's huge potential mitigation from these. I want to bring in another agriculture angle here and say, in this analysis, this reforestation is attributed as a forest practice, maybe because the lead author is a forest person, but actually the only way that tree planting could occur is that land agriculture became more efficient, as Dr. Lau mentioned, reduce the area of agriculture, increase sustainable intensification, and free up land for afforestation. So we could equally call reforestation kind of an agricultural mitigation in that sense. Within agriculture, there are, of course, many management options. Some of the bigger ones from this analysis were avoiding conversion of grasslands, using cover crops, biochar, and then alley cropping. Alley cropping is growing rows of trees between rows of tilled agriculture, so widely spaced rows of trees. We've heard a little bit about cropland nutrient management, and of course, manure management and other practices. So for some of these practices, we need better data and we need better tools for assessing the benefits. And again, just a reminder, when we say benefits, we want to be thinking, as Dr. Lau mentioned, in terms of ecosystem services, or we want to be thinking in terms of air, soil, and water quality. So I've mentioned a few of these practices. There's also feed additives to reduce enteric methane. And that's a very active research area now, and we hope there'll be great progress shortly. Right now, we cannot quantify that potential benefit because the research is ongoing. I also want to say that in case our job isn't hard enough, dealing with agriculture and forestry and air, soil, and water quality, we do need to be also thinking at the system level. If we could cut food waste in half, it's about a third of food is wasted currently. If we could cut that waste in half, we could free up an immense amount of agricultural resources that were used to produce that wasted food. So think of 15% of agricultural resources all being thrown away. So we need to be addressing this issue at the food system level. And we need to be thinking about connecting farms and forests, connecting livestock with crop production. So here's just an image in New York State of forest regrowing on former agricultural land. We need a range of tools to help farmers, ranchers, and foresters mitigate and adapt to climate change. So we've heard discussion at the individual field level, crop rotations. There are other management practices at the farm scale, which might require a different model or a different set of tools. And then when we think about the regional food system scale, that's probably a different model than we're using for an individual cropping system. And of course, we need to tailor these tools to the user and the context, such as whether it's a field scale or a national scale assessment. And we'll hear more about that today. And I would suggest we also want to think about some very simple tools that we can give people that might look more like a fact sheet or a recommended list of practices. And then in some cases, we need complex simulation models as well. So in conclusion, here are some things that we know and some things we need to know that I think we should pay attention to. I won't read through all of them, but again, just emphasize that none of us can think about everything at once, but together we do need to be thinking at the system scale as well as at the field scale. So thinking about the food system and thinking about waste systems. And thinking about what farmers know and think about climate smart agriculture from the previous speaker, we need to think about tailoring the tools and the way we communicate the results and the analysis to different audiences as well. So I look forward to the panel discussion that's upcoming. Thanks very much.
Peter, thank you so much, and appreciate that context very much as well. And Steve and Stefan, I'm going to hand over to you.
Okay, give me just a moment here.
Okay, thank you very much, Terry, for the opportunity. And Steve, Ogle, and I are going to kind of go back and forth with this presentation. I'm going to do the first set of slides. So there's the title. I'm not going to read it again. But one thing to point out is a lot of the context of our presentation is our national greenhouse gas inventory, which is crucial for our commitments to the United Nations Framework Convention on Climate Change, as well as our nationally determined commitments for the Paris Agreement. Okay, next, please. So Peter just showed a very similar slide. So yeah, just to make the point, nitrous oxide from the crop and graze soils, it's basically the soil fluxes are the biggest agricultural source in this country. So that's a lot of what we're going to concentrate on. Next, please. Now this slide it's kind of a manifestation of the title for the the overall perspective. So we have these, what goes into our models, different databases, observational data, management and other activity data, our understanding of the processes that contribute to emissions. All that knowledge and info gets fed into the model. And then there's important model outputs or products like the greenhouse gas inventories and mitigation potential estimation, as well as decision support tools. Okay, next. So the overall outline for the presentation, or overall modeling framework, the observational data that we use and how we calibrate the model, and then the activity data used to run the model, for inputs, concentrating on the management information, and then some of the results in terms of the inventory, and then lastly, some suggestions for improvements. Next. Okay, so the overall platform, there's really three main parts here: the model development and calibration, which again is crucial. Crucially depends on the observational data, and then the process understanding in the model. So the model simulates the plant soil processes that lead to productivity, grain yields, forage yields, as well as the soil greenhouse gas fluxes, soil carbon changes, nitrous oxide emissions, methane fluxes, and then the different databases that are used for the model inputs. So we run the model, everything from the site level to regional to national to global scales. And there's different databases that we need to acquire the inputs to run the model. And we'll look at all these individually. Okay, next. So just to show in IPCC terminology, tier 1 is the simple emission factor spreadsheet models to estimate emissions. Tier 2 is more, tier 1 is based on global analyses. Tier 2 is still emission factors, but more nationally or regionally derived data, versus tier 3 emphasizes process-based models, and pretty well established as you move up in tiers, your uncertainty bounds tend to shrink. And this is just one example. There's lots of evidence to support this idea. Okay, next. And here's some recent model results. So most of our model calibration and evaluation is done with site level, ground level observations. And we say that Descent is a bottom-up approach because it's based on what's going on the ground, and measurements at the soil, with soil measurements and soil surface measurements, versus another way to estimate gas fluxes, in this case nitrous oxide, is to use atmospheric inversions, where the atmospheric chemists monitor the changes in gases at very, very small time scales and account for wind speed and other factors, so that they can infer through back calculating what the surface flux is. And so this is a pretty cool diagram showing the seasonality throughout the year. The red line is from Descent simulations of that purple rectangle where a lot of the agricultural land is in the country and is responsible for a lot of those N2O emissions that are in our inventory. And then the gray is inferred from the inversions, accounting for their uncertainty. And Descent's going pretty well. Both methods are showing the springtime pulse around day 70 associated with freeze-thaw cycles in the northern part of that rectangle. Then of course you get the hump around day 150, the beginning of summer, associated with fertilizer additions. And the fact that these two methods are converging and showing pretty similar patterns, we think is encouraging. Descent tends to be lower than the inversions. One reason for that is Descent's just on the agricultural soils, versus the inversion signal is getting all the other sources, so the indirect N2O, industrial N2O, and so on. Next, please. And so that springtime pulse, that's a new, relatively new addition to the Descent model. And then just showing the implications for that. So this is running the old version of Descent before the freeze-thaw algorithm, and then the current version we're using for the inventory, taking that difference. So this is just isolating the freeze-thaw enhancement induced emissions. And so you can see the spatial patterns. You have to be far enough north. The southern regions don't get enough frozen soil days accumulated or don't get a snowpack, so you don't get that springtime pulse. But you also need some nitrogen additions. And you put this all together on the national scale, it increased our estimated nitrous oxide by about 10 to 12% on average. Next, please.
Okay, I'm going to talk a bit now about the emissions observations and calibrations we do with these models. And that's focusing on the left side of this diagram that Steve introduced a few slides ago, where we're focused on linking these two. And central to all this are our observations. And one of the main networks we use is called GraceNet, or Greenhouse Gas Reduction through Agricultural Carbon Enhancement Network. And that map shows you the sites around the country that are included in that network. The observations are central to the modeling we do at the national scale. Without this, our results wouldn't be as meaningful, let's put it that way. With this, we've developed a model selection and parameterization, a Bayesian model analysis platform, if you will, here at CSU, which we use to develop new algorithms in the model. We can also test other models. We've had a recent project funded by USDA looking at DNDC and ASIN. And we can also just calibrate models in this platform. The centerpiece of this is this Bayesian calibration in the middle. I'll talk a bit more about that in a moment. And from this, we can then run forward Monte Carlo uncertainty analyses to assess confidence intervals in our results. It's a little bit more about the Bayesian calibration. So we have a group of parameters in the model that drive, for example, soil organic carbon dynamics, or what we're modeling there. And there's prior distributions of those parameters. And on the step one here, we randomly select some groups of those priors, and some of those are useful. They're informative relative to the measurements, telling us about the reality of what's occurring in agricultural soils. And those would be the green ones in these circles here. The gray ones would be ones that are not as informative. They don't produce accurate results. But we don't know this a priori, what's good and what's bad, if you will. So in step two, we then run the model with these parameter sets from these prior distributions. And we then evaluate those results against measurements. And those that more closely match the measurements from the experimental network like GraceNet then get filtered through and become, in step three, our posterior distributions for these parameters. And so this process allows us to refine those distributions. And this is an analysis we published a couple of years ago looking at that modeling soil organic carbon dynamics. And I'm not going to go through all the details here, but that dashed line represents those prior distributions that we developed for the model. And the gray area, shaded area, represents the posterior distributions. You can see some of these, like the temperature effect there, B at the top, it was well informed by the measurements, but other parameters were not, such as down at the bottom in the middle, H, was the water effect on decomposition. So anyway, from this, we're able to refine some of these parameters, their distributions, that is, and reduce our uncertainty. The next thing that we need to run the model and to produce these national estimates are our management activity data. This is central. And this is on the right side of the diagram here, the geospatial data sets and the surveys that we're using. I want to talk a little bit more about those now. When we think about what we're doing, we use a survey, and I'll talk a bit more about the survey here in a moment. We're essentially modeling farm fields all around the country. And for each of those fields, we need to know something about how they're managed. And this could be an example of a field where you're growing corn, where there's a tillage practice, maybe sometime in the spring, and then a planting a few weeks after that, maybe with some starter fertilizer. A few weeks later, maybe a month later, you're coming back with a second fertilizer, split application. And then later in the summer, you're harvesting that crop, and maybe there's a manure amendment in the fall. We need this time series of data all the way from 1979 to 2020 to drive our national inventory analysis. So a little bit more about that survey. We use the USDA's Natural Resource Conservation Services National Resources Inventory, or NRI for short. And this is showing you the red areas here where there's more cropland in the country from this survey. And of course, that's in the upper Midwest, the central part of the US. If we focus in on an area here, maybe in Southwest Minnesota, and that little blue star there, this might be the landscape you have there. And those three crosses represent three NRI survey locations. And the one on the left there is in a crop field. And we would be modeling that crop field as part of the national analysis we do. And from NRI, we get the land use, which is cropland. The crop is corn in this case, and whether it's irrigated or not. But we need other information as well. So we look to other sources. For example, we use the MODIS Enhanced Vegetation Index from NASA to tell us something about the greenness of the canopy throughout the growing season. And this helps constrain our net primary production calculations and eventually the yields that we are predicting for the model. We use PRISM daily weather data from Oregon State University to get our temperature and moisture precipitation data, if you will, for the day. And we use the Sergo soils data from USDA NRCS to get our soil characteristics. For example, the texture, maybe in this case, it's a clay loam. We also need planting date and harvest date, as well as the tillage practice, fertilization management, manure amendments, and cover crop data for this national analysis. And we get that from a variety of sources that you see here. We use USDA Census of Agriculture for some information. We use conservation technology information center data, particularly tillage from the 1980s and 1990s, comes from CTIC. We use the USDA NRCS's Conservation Effects Assessment Project data, or CEAP for short, and that gives us a whole suite of practices that have been collected through that survey. We use USGS's fertilizer database. This is a sales database, so it gives us an upper level constraint on the amount of fertilizer that's applied in the simulations. We use USDA's Agricultural Resource Management Surveys, or ARMS, which gives us several pieces of information, for example, fertilizer rates across the country. And then more recently, we've been using a product from Regrow Agriculture. It's a remote sensing product called Optus that's giving us tillage and cover crop data. So we have a variety of information that we're combining here through a statistical machine learning method. Random forest, for those of you familiar with machine learning methods, is what we're using, along with a few other methods to trend these data over time. And I'll hand it back over to Steve to talk about the results.
Okay, so next, please. So now we're going to concentrate on that bottom. Yes, some of our products are at national level inventory greenhouse gas flux estimates. Next, please. So this is an example of the Delta soil carbon reported in the recently published inventory. So first thing to realize is it's from the point of view of the atmosphere. So red is positive numbers. So positive means a carbon source versus negative numbers are sinks. And so you look in Florida, in other parts of the Southeast, you have some red, and some of that is due to drained organic soils that are carbon sources. But then you look, say in the upper Midwest, Illinois, Iowa, some of those counties are carbon sink. They're mineral soils. There's been improved management, say reduction in tillage intensity, improved crop varietals. So when you put this all together at the big scale, the mineral soils are a sink, the organic soils are a source, and in aggregate, our best estimate is that we're still a sink in aggregate, but the confidence interval kind of intersects zero. So we're in aggregate, our soils are roughly carbon neutral currently in this country. Okay, next, please. And then there's this question of attribution. I think Tim Ryder even mentioned, well, how do we know some of these CRP programs, what have they done from a greenhouse gas perspective? Well, we can address those questions with the model by doing a series of model runs under different business as usual versus different management practices that have been implemented versus doing counterfactuals, pretending that nothing changed starting in 1980. So, and this is the kind of result you get. So a few things, what stands out is the conservation tillage, reduced till and no till. Again, from the point of view of the atmosphere, negative is a sink. So there's some, some fairly significant carbon storage, not near as much as the forests. The forests are the big sink in this country, but the soils are making some contribution. And some other things, we look at the top with the triangles and the cover crops, they're not having much of an impact. And I want to take that to, I want to interpret that to mean that cover crops don't have any potential to store carbon, but that's largely a function of the acreage is so small. So this is at the national scale. There's been many, a large portion of the farmland has been converted to reduced till, very, less than probably 2 or 3% includes cover crops. So maybe there's, so the cover crop effect is just limited by the lack of acreage. And maybe a caveat with the conservation tillage sink. If you think back to Raton's slide, showing the depth distribution of carbon in the soil with no till versus conventional till. So this is just for that top, say 20 to 30 centimeter layer. So we feel pretty confident saying the reduced tillage is giving you some storage in that layer, but that's sort of a limitation of the model. It's only doing the soil carbon dynamics in that top 30 centimeter layer. Okay, next, please. And we just showed some of the sink strength of carbon, but now back to the big source, the nitrous oxide, to just show the model generated results. You know, N2O, the emissions are big where you think they would be big in the Corn Belt region, where you have lots of inputs from fertilizer and rotations with soybeans. You know, the lower Mississippi Valley, where there's some pretty intensive cropping. You know, of course, California and some parts of the Southeast. So, yeah, to a large extent, you know, the spatial patterns are driven by the nitrogen inputs and the cropping intensity. And then you get interannual and variability driven by weather, but this is just really showing the spatial patterns. Okay, next. And remember, from that pie graph, you know, methane, you know, is a source in this country. It's not a huge player, but in some counties, again, the lower Mississippi, some of those states and counties, the methane from the rice is a pretty big source, as well as some parts of Northern California. So we want to emphasize, yeah, doing the complete carbon, methane, and N2O. And lastly, yes, Stephen Ogle is going to finish up with some improvement suggestions.
Yeah, and I would point back to Peter's talk. I think the main methane emissions, of course, are coming from the livestock, so not so much from rice cultivation here in the U.S. Yeah, just a couple of improvements I wanted to mention here, and one is enhancing the Bayesian calibration and model testing. So while we have a nice network of experimental sites out there, it's really a fairly small area, and maybe around 80 to 100 sites, as I recall, that we use for calibrating the model. When you think about the area of agricultural land here, it's really not that much that we're sampling. So given this limited number of observations out there, we're very hopeful about this soil health monitoring network or soil carbon monitoring network that Bonnie mentioned earlier this morning. We're looking forward to seeing those data in the future, hopefully N2O and methane and of course soil carbon data there. I think expanding our experimental network is really important too, because we go out and we test new ideas there, new mitigation technology. So we stay on top of that and can address those in the inventory as farmers start to adopt them. And then, of course, further model testing and evaluation, like the work we've done recently with DNDC to compare our models and hopefully improve them. And the other thing is our management activity data. This is just a short list of some of the missing data we don't have. We don't have any data on agroforestry on the left side here. We don't have data on livestock grazing practices, even though that's emerging in this regenerative agricultural paradigm. We don't have any baseline data for grazing across the country. We have a lack of data to address some of the key fertilizer management practices, like some of the enhanced efficiency fertilizers. We also have a lack of continuity in some of the existing data collection, that it's not collected very often, like SEEP, for example, great data set, but it's only collected about every 10 to 15 years. And we have no data collection so far on biochar, which is not being used a whole lot at this point, as we understand, but we need baseline data. We need to start collecting that information. And with that, I'd just like to thank you for your attention. And I will just acknowledge a few people, Dr. Jay Bright and Bill Parton, who help on this project, research staff that work tirelessly with us to complete this inventory every year, and of course, funding from EPA and USDA.
Well, thank you both for the presentation and for the exhaustive work that you do from year to year to year. It's such a critical resource for everyone. Keeping an eye on our timeline, I'm going to go directly, Sarah, and ask you to take control of your screen and take it from there.
All right, hello everyone. All right, can you hear me and see my slides, most importantly?
Yes, yes, and yes.
Marvelous, okay, so hello everyone, Sarah Rell, US EPA, and I thank the AgMIP team for having me today and putting me right in after Peter and the Steves, if I may, because I think my talk will go very nicely after their talk on the inventory and modeling that goes into some of that. So just a little bit of my talk today and just kind of the very high level context of our work and some recent projections, and then some thoughts. And the views expressed are my own and not necessarily of my agency. Always have to put our disclaimer on there. So as you are all well aware of the current context in which we're working, there's a lot of talk about CDR technologies, carbon dioxide removal, natural climate solutions, nature-based solutions, all these things swirling around. But one thing that we certainly know is that within the context of reducing emissions over the next 10 to 20, 30 years, there's a lot of opportunity from land-based solutions, and both via carbon stock, sequestration, as well as, in potential of biomass and BECCS. And, not only in recent reports that we've seen, IPCC, et cetera, but also in our national commitments that Steve Grosso mentioned earlier, reducing our emissions to net zero and here in the United States by 2050. So just a little bit about our work. We are here at EPA in the Office of Air and Radiation, Atmospheric Programs, Climate Change Division, and the Climate Economics Branch. So buried down below in the belly of the beast, if you will, of the Climate Economics Branch. And our branch does a lot of work looking at the economic, greenhouse gas, and other effects of rules, regulations, and also doing a lot of just research and model development, et cetera, in the world of greenhouse gases with a slew of different tools. I integrated assessment modeling tools, sectoral models, national, global, more sub-regional, all the way to different perspectives from modeling, intertemporal optimization, as well as recursive dynamic. We have a lot of different tools at our fingertips that we've worked with for many years and developed, and a long history in the land use space, looking at greenhouse gas emissions and potential mitigation, and also greenhouse gas accounting. Both our inventory team, our sister branch, compiles the U.S. greenhouse gas inventory, working a lot with CSU and USDA and others. But in our shop, we do a lot of the projections work, and a seminal report we put out in 2005, you might be familiar with, on potential mitigation from ag and forestry in the U.S. 2005, and then in 2009, the Waxman-Markey analysis of climate on the Hill. Working with various partners, interagency partners on our climate action and biennial reports, the U.S. mid-century strategy, et cetera, then more recently, the long-term strategy projections. And then other parts of our portfolio here are the Clean Power Plan, the role of bioenergy in that, and some other analyses related to emissions associated with biomass use for energy. A lot of our work over, when I first started in 2009, was focused on carbon market designs and how we look at different things like Peter mentioned, leakage, additionality, et cetera. And it's, we're circling back. So we have our tools at ready. Excited to work on this stuff as we have been over the years, and couldn't be here without a lot of our collaborators at The Ohio State University and University of Idaho, NC State University, Research Triangle Institute, Texas A&M, and of course our interagency partners, USDA, Forest Service, DOE, et cetera. So with all of that context, why land use related greenhouse gases and sequestration is important, but why is it so challenging? Well, a lot of our data does change. We have heterogeneous systems in the US. We have improvements to our inventory over time. So this is a graphic I had in a paper in 2019, just, graphic we put together every year. The data is improving. We get more of it, and every year we calibrate our models, et cetera. So it does make it difficult when you're trying to not only, figure out what data, updating your models, our projections tools and others to the most recent, the latest and greatest data, historic data, but then also how do we set targets versus a base year, let's say 2005, for example, when that itself can be a moving target. So we have, systems that are spatially different, biophysically different, but then also markets. We look a lot of how markets can affect prices and affect our land use and management and the related greenhouse gases. So this is just a Sankey of the different wood flows in the US that we did a few years ago. And then again, trying to take these two, components full of variability and put them together for projections for USG reports is quite challenging, but nonetheless, we have to do it. And, we know no model is perfect, and they don't, predict the future. Don't like to use that word when I talk about projections, but it gives us ideas of what the future may hold and helps inform policy. And we have different tools that we use, different kinds of tools that give us different kinds of estimates. Some tools give us total biophysical, this is what the biophysical on the landscape may give us. And then we can add, okay, what's the techno-economic potential? It kind of slides the map curve a little bit, the abatement cost, I should say, over. And then if you add it in market potential, okay, what are the competing demands for this product or for this landscape or for this, raw material? And then when it starts competing with other markets or, within agriculture, for example, if you just have one crop versus multiple crops in the market model, and then you actually add potential competition with other markets like bioenergy and forestry and all these things, that actually reduces the abatement available at certain price points. So one thing our work is really focused on in our shop is how these economic interactions allow us to think about trade-offs of resources, of land, of money, et cetera, human capital, et cetera. So specifically in our land use team here, we have a range of tools within the land use area. Give that, I said earlier, it just gives us an idea of potential future magnitude and directionality of outcomes. What will the future look like if these certain conditions are in place or met? It gives us an idea. We can look at, what policy designs may or may not work, or what can we tweak in a policy design to get a certain outcome. And then also looking across a range of models is very helpful, because you can, look at the uncertainties. Like if one model is saying one thing, as a baseline, for example, and another model has a different one, but the overall magnitude of mitigation potential from certain portfolio of options is similar, that's a good sign, right? So having a range of models is really helpful to let us look at, okay, how do we evaluate uncertainty? How do we evaluate the impact of a policy design, et cetera? So this is our suite of tools. I won't go through all of them in depth. We have the land use resource allocation model, a spatially explicit partial equilibrium model of the U.S. forest sector, developed by Greg Latta out at University of Idaho. The forest and agriculture sector optimization model with greenhouse gases, a mouthful that I had to learn a long time ago not to trip over. The FASM model that you might be familiar with. It also looks at forestry and agriculture together. Global timber model, global model of forest resources and timber markets, and the global biosphere management model out of YASA, a detailed global model of ag, forestry, and land use. And all of our models are currently aligned to the Forest Inventory Analysis Project out of U.S. Forest Service, which also informs our U.S. greenhouse gas inventory. So again, I won't belabor this, but we basically look at our baselines and alternative scenarios, those alternative futures, different parameters, different kinds of policies, and allow us to see those potential outcomes in terms of greenhouse gas emissions, but also land use change and other things. This is from a recent paper that we did with Research Triangle Institute, looking across, okay, these are the baselines across different socioeconomic conditions of the SSPs and the different portfolio of greenhouse gas emissions and fluxes. And then we added on a carbon price. So then you can kind of tease out, okay, what is the carbon sink driver? Is it socioeconomic drivers like population and GDP, or is it more from the carbon price, this blue line? So some recent work that we've been doing in this space. Laura, stepping through them real quick. Laura gives us spatially explicit information about, okay, looking at the plot data from FIA, pulling it into this geospatial matrix that we have, and it has roads, it has transportation costs, ports, you name it. We can do all sorts of analyses looking at, okay, how do we move that forest resource through time across site classes, forest types, and can really drill down and do like really detailed analysis across border interactions in New England and New York in one of these analyses that we did with Greg. And so this allows us to kind of look, okay, what happens on the actual landscape, and we can take that information, we aggregated it up into the FASM regions. So we can do more regional analyses and national analyses with an intertemporal optimization model. And allows us to do some of these, more longer term policy simulations that we can't yet achieve in the LoRa model. Recent analysis that we did with FASM and GTM, the global timber model again, just looking at, okay, if we have certain expectations in the future and different carbon prices, et cetera, overall harmonized drivers, what kind of future mitigation can we get across our forestry portfolio? Even though the baselines do differ, we did get a very similar range of mitigation potential over time, which is an exciting response when you're looking at future projected outcomes. One project that we're currently working on is updating our 2005 mitigation report, that seminal report, in the works for a while, but we're really excited and we're getting closer to actual fruition. It applies FASM, GTM, and the globe biome model. So the previous report only had one model, the FASM model used. And so we're kind of getting more in align with AgMIP itself, EMA energy modeling forum, LUMEP, and others to better understand, okay, how do these models compare, but also how does it help us assess leakage and additionality, especially when we're now going to be using a domestic model as well as a global model, so we can see how that, the different scales involved and trade assumptions, et cetera, can affect our mitigation portfolio here in the United States. And just some initial max that we got, marginal abatement cost curves. These are old results, so don't cite, please. You would be wrong when the final report comes out. But just some of the ideas of, okay, what are we seeing across the models? We work a lot with various partners, but I did want to just highlight some of the work we do with USDA and USDA Forest Service to look at greenhouse gases. We've been co-hosting the Forestry and Agriculture Greenhouse Gas Modeling Forum. Since 2001, we host that every 2 years, traditionally at out in West Virginia at the NCTC, but been virtual lately. And if you haven't heard of us, we hope you'll look us up. It's a great forum for discussion and collaboration and talking about new advances with modeling and greenhouse gas mitigation, both biophysical, but also economics. Since 2003, we've worked closely via an interagency working group with USDA and Forest Service to take our different suite of tools, because they too have a suite of modeling tools, and bring them together to produce the U.S. greenhouse gas projections for lands. So doing that under like the long-term strategy and other the climate action report, et cetera. So first time we did it was in 2014. Coming together, that's the first time the U.S. actually put forward a range of mitigation for the future expectation, just to recognize the uncertainties associated with the land use sector. It hadn't been done before, but it was actually a really exciting way for us to be transparent about the uncertainties. It was a new process, some familiar faces, new people, and a lot of pressure from the White House at that time to deliver, but it worked out really well, and it continues to this day to be a great working relationship. So we did it in 2014 for the CAR, and then the BR in 2016. Our U.S. mid-century strategy, we worked closely together to come up with some of the mitigation opportunity and potential there, as well as in the most recent biennial report released by the current administration and our long-term strategy. Other efforts that we're working on right now is we have pretty soon the next round of U.S. government reports that we'll contribute to, including the next biennial report. And then also FORMIP, modeled after, guess what, AgMIP. We have a forest model intercomparison project. It's a very small community of forest sector modelers that we've been working together with, but it's been with GTM, GloBiome, and the Global Forest Products Module, which I believe Forest Service, it's been renamed since we worked on this project or started it, but that paper hopefully will soon be coming to press near you, that we can share a range of really exciting opportunities that we saw in the projections across these models working together in a harmonized fashion. So I won't go too much further, but I did want to, in terms of time, but I wanted to echo, the Steves, if I may, about our ability to take data and find areas where there are gaps. Currently, we're going back to some of the voluntary greenhouse gas market and technologies. How are we going to be putting in some of the emerging market trends? We have very different market programs right now, from like NCX to the California programs. How do we put all this in terms of modeling in the future, these voluntary models as opposed to mandatory programs? Spatially explicit model being a big thing right now, being able to drill down and kind of see what's going on and landscapes at the project or larger level, landscape level, which a lot of us use. And then how do we, design these these different modeling exercises to look at leakage, to look at like how do we incorporate MNRV? How do we, take in some of this new empirical studies to improve our understanding? I think, Steve Ogle's point about making sure we have more on agroforestry, as well as biochar. There's areas that we'll have to include at some point in the inventory, but there aren't IPCC guidelines, I think, Steve, right now to put in agroforestry into the inventory. So how do we go about doing that when there aren't established guidelines? And then, as I said, the mitigation report, we're looking forward to it. And also, any future collaborations. We're always looking forward to new ideas and people to work with and leverage the work we're already doing with work that you're already doing, both in AgMIP and outside of it. Because we know that lands and forestry in the United States and globally have to do have a big role, expected role in achieving our goals, as Steve Del Grosso said. So I think, having this kind of opportunity for all of us to get together and talk about our various research applications, et cetera, is one way to help us get closer to achieving those goals. So with that, I'll wrap it up and say thank you very much and look forward to the conversation.
Well, thank you, Sarah, and thanks to all of you for your great remarks and sharing. There's, again, so many things to cover. It's hard to know where to pick up and where to start. Just a footnote, a personal interest, one of the things I know I'm looking forward to is expanding our discussions with the forest modeling community and looking for the opportunities to help or complement your work in developing those intercomparison capabilities. So really look forward to seeing how those discussions unfold. And a pet issue, and we're a year or a decade away from being where we'd like to be on that, but being able to develop a capacity to do that what if scenario looking across agroecosystems. So if we put more land into croplands or we take more land out of cropping, as Ratan was suggesting, then what are the options and what are the impacts as forestry or grazing moves into some of those spaces? So how do we look at those interactions between the different modeling efforts that are already underway? One question came in, and I'll pass that one on. And this is from Danielle, who is in turn picking up on a question from Ali Fair, and it's in our chat box. And the question is, as we look at limited resource farmers and ranchers, as opposed to the big mainstream producers, how do we balance between looking at those smaller producer needs and impacts against looking at getting, quote unquote, more bang for the buck when you look at larger production? And I guess the question is to hear what others think about the efficiency equity question, and how do we get an optimal portfolio of looking at small and large operations, and what does that mean for science and incentive programs? So that's a very heavily loaded set of questions there, but any comments would be appreciated.
And maybe I'll just interject to say we are likely to run out of time before we can answer all these questions, but the panelists should have access to the Q&A to add their further thoughts on these questions and others that you might find there. So the floor is open to the panelists for answering this question.
And Peter, I'm just going to throw it to you to start off with, if you don't mind.
Okay, so I think we're addressing kind of the challenge of balancing equity for maybe smaller producers versus efficiency for larger producers. I'm not an economist, and I don't study this topic, so my opinion, you can value my opinion given that information. My simple-minded response is that equity issues have developed over a long time with complex social systems. So I would say those are issues that need to be addressed and probably need to be addressed directly. In other words, we are interested in more things than just carbon, and we need to address more issues than just carbon. So I acknowledge the issue, and I guess I would just turn it back to say there are things that, in my opinion, that we can do kind of within current kind of business structures that people are used to, and there may be things we need to be thinking about doing outside of those to address goals such as equity.
Sarah, any thoughts on your end? I know that's not the heart of your focus here, but just curious, any reflections?
I saw Mark on mute. I don't want to make sure he had an opportunity. Mark, did you want to go?
I was just going to point out that when we look at adoption of practices, some of the smaller farmers can actually be a little bit more nimble. Not that large farms can't do some of these things, but they've got, I'll say, more time crunch, just covering more acres, right? And so smaller farmers a lot of times have the time to be able to put in, to learn that knowledge gap that exists when you adopt. And so a lot of times we do see that. Is it right? No, because, well, if I think of, just trying to meet the needs and the number of acres that need to be adopted for various practices, that's likely not going to be met with the smaller farmers. But from an innovation adoption curve perspective, they can be the innovators that can help us move that needle down the road.
And I'll just pipe in again, thinking as an economist also, but also with the broader perspective here, knowing that where we are with the climate crisis, and as an economist, the biggest bang for the buck sometimes is the philosophy of let's get everyone together and have these kind of seminars to teach a man to fish, that using something like that, like let's all get together, spread the technology and have more information out there. And there's a lot of different organizations now coming at this from different angles, whether you have it's the dairy industry, with their own GHG reduction goals, you have EPA, we have all these different groups that are engaging, and especially thinking about in terms of equity and access and equity, environmental justice, et cetera. I know our agency and others, the federal family, if you will, are really looking at this and trying to make sure programs are taking into account access issues, and that is a huge issue and a huge barrier to many. So we're actively aware of this and trying to think about, okay, spreading dollars across all sizes of farms, across all people, et cetera, is probably a top priority, I would say. And again, not speaking as the environmental justice part of our agency, but just as from my perspective as a technician, it's been a huge priority for us. And I'm sure my other colleagues across agencies would agree that, look, everyone, all hands on deck, I think is where we are, small or large. And I think having, more information out there is better to get more people on board to actively participate.
Fantastic. And
yeah, I wanted to bring it back to some of the AgMIP modeling kind of needs or approaches or potentials here. And to me, it comes down to two questions. So the first would be addressed at Stephen and Stephen around the use of remote sensing and a variety of statistical and data packages to create that set of inputs that go into your model. And I'm wondering if that's something that is well known and established and treated as a public resource, or if it's something that doesn't get outside your own institution's walls, because I see there being a great need for us to, if we are going to do intercomparisons, or if we are going to put crop models next to the carbon models, how do we share those sets of information so that we start from an elevated, foundation? That's the first question. I'm going to turn to you in one moment. The second question turns towards the future, which is about scenarios. It's a similar question. How do we come up with scenarios that are consistent across our various approaches here, and think about carbon, but also the economics, productivity, other motivations for the agricultural sector, and not to mention FORMIP or other programs that might be in this space, and the need for a process to make those scenarios recognize equity, justice, and all these other things that have come up. So I guess I've seeded those two questions. Stephen, over to you, please.
I'll respond to the first question. So some of the data we use are publicly available, but not all of them. The data that we use from NRI, for example, is we obtain it through a confidentiality agreement, so we can't just share it as it is. However, we can aggregate it, and the NRI program is usually willing to work with us on this to a larger scale and share the information. And that's because it's information on individual farms, and farmers don't want that information just being, openly available to anybody out there. Some of it, at least, is proprietary. So we have to be very careful. I think there probably are some opportunities maybe to create something at a larger scale that would still maybe meet the needs of a model intercomparison. anyway, so I'll stop there. And maybe I'll let one of the economists here take the second question about the scenarios.
I think you passed the mic to me, Steve. And it's a great question. I mean, that's one of the things that we struggle with sometimes is, we have so many tools, and yet how do we design the scenarios to answer the questions we're seeking to get to, right? And do we have even the data necessary to answer the questions that are before us? So one of the things I recall back in the Waxman-Markey days of the climate change legislation analysis we did back in 2009 was, we have all these different kinds of bills coming forward, HR 2454, Stabenow bill, et cetera, that had these slew of new mitigation opportunities in ag and forestry. And a lot of us said, we don't have data on this, let alone how do we build this into a scenario, let alone a scenario that allows for voluntary market participation because it's an uncapped sector. So a lot of these questions over time that we get those questions, and now, 13 years later, we're actually in a position to better answer some of those, but it's taken a lot of time and money, data collection, model development, et cetera, to now be able to design, for example, voluntary market construct within our modeling suites, like taking data from Steve and his team, putting it into our model, and then being able to say, okay, if we have some agriculture producers participate in a voluntary market, but the others don't, what happens on the landscape? Is there enough leakage that it doesn't really make a difference? Or maybe there is a big difference because you get social pressures as well, but it's hard for us to capture that in the models as well. So I don't know if I'm really answering your question on scenario design, but more some of the struggles we deal with trying to even, okay, yes, we know what the question is before us, but do we have the ability to even model it and design the said scenario? Right now, and a lot of the work we've been doing is thinking about, okay, with our US commitments before us, and we know right now what the tools that we have for the most part in the US, except for the aforementioned agroforestry, biochar, et cetera, but for the big bites of the pie, if you will, for mitigation, we can think about where can we focus our dollars, in a way that will actually get the biggest bang from the buck from our other person questioning earlier. So from our perspective, it's just trying to figure out, okay, what opportunities are out there, but then also what kind of policy levers need to be in place to actually achieve what the scenarios are telling us. I hope that wasn't too convoluted of an answer.
Thank you. That's useful. I think there's a process that can help with this national scale and local scale. I'm going to just also read another question from the Q&A here. Comes from Doji Adziandeke. I hope I'm pronouncing that close to correctly. And this question about the response of carbon sequestration to climate variables. So specifically asking if there's a paper, but I wonder if people can speak more broadly. A lot of times carbon sequestration is thought of as in aggregate or over a long period of time, but there is a year-by-year variation there. And I wonder if people can say, does it happen more or less under drought conditions, more or less under hot conditions? The climate is no longer stable, so is the sequestration potential going to go up or down? Any thoughts along those lines?
Yeah, maybe I could respond. I think this is actually a really good question and really challenging to address. And there's a paper that came out, I believe, out of one of the German groups, maybe Jena, where they simulated forward and they found, as I recall, losses of soil carbon in the future. But that could be tied to many things. It could be, of course, the change in the climate itself impacting the decomposition of the soil organic matter, but also what's going on with the crop and how productive is the crop. And I know earlier today there was discussion about genetics and then you think about that and what's going to happen in the future, because a lot of times when we do these simulations, at least those of us in the biogeochemical modeling community, we're not thinking about the crop and how it might change. We're assuming it's like today, but probably not, right? Crop breeding is going to continue. There's continue to be improvements, and so that's equally important, I think, to address this question about what is going to happen to soil carbon in the future. and then all the mitigation options that are out there and how they impact the soil as well as the crop in these systems. So I don't think we have an answer for this today, but I think we've got a lead, and there are things that we can look at in the research community to address it in the future.
I'll chime in on this briefly if I could. Certainly challenging to think about climate change impacts, and people, of course, are modeling those impacts on ecosystems and publishing on that all the time. We can see the increased forest fire incidents over the last couple decades in the US as an example of some ongoing change. And there are publications looking historically at mega droughts, and that they have occurred certainly in the record, and we can expect more in the future. I think one aspect that we can maybe try to narrow the uncertainty a little bit here, and might also be appropriate for considering scenarios, is thinking about the kind of risk management and uncertainty aspects of this. So trying to use those as information. Are there practices that we have good information that these are more robust over time and space, more robust to climate change than other ones? And just the example of soil carbon being a bank where carbon's going in and out, right? As opposed to perhaps soil inorganic carbon or enhanced rock dust weathering, if that's a process that is longer term active research going on. But so this may not be the best example, but if there are biophysical characteristics that we can identify that help us say, hey, these practices are more robust to various conditions, that might be something we think about in developing scenarios and, in fact, in promoting practices.
Thank you each for wonderful comments, and look forward to some follow-up discussions in the not very distant future. So much again to explore.